Assalamualaikum warahmatullahi wabarakatuh. Today we will going to discuss about sequence and the limits. Okay, before that, let me introduce ourselves. Let me introduce our group. We are from group 6. The member is Dwi Sri Lestari and me, Ilham Roziqun Nafik. Okay, in here, okay, next, in here we will discuss in part 1, definition, a sequence of real numbers. A sequence in a set S is a function whose domain is the set N of natural numbers and whose rank is contained in the set S. Okay. A function defined on the set natural number set uh, whose rank is contained in the set real numbers. In other words, a sequence in real number set assigned to each natural number n equals 1, 2, 3, and etc. a uniquely determined real number. If x is a function from natural number set to real number set is a sequence, we will usually denote the value of x at n by the symbol xn rather than using the function notation xn. Okay, the values x and are also called the terms of or the elements of the sequence. We will denote the sequence by the notations like this. Of course, we will often use other letters such as y, uh, y, z, and so on to denote sequence. Okay, next. Sequence are often defined by giving a formula for the nth term xn. Frequently, it is convenient to list the terms of a sequence in order, stopping when the rule of formation seems evident. For example, we may define the sequence of reciprocal of the even numbers by writing x equals a half, a quarter, 1/6, 1/8, and so on. Third, a more satisfactory method is to specify the formula for the general term and write x equals 1/2n for n elements of natural number sets, or more simply, x equals 1/2n. Another way of defining a sequence is to specify the value of x1 and give a formula for xn plus 1 for n greater than 1 in terms of xn. More generally, we may specify x1 and give a formula for obtaining xn plus 1 from x1, x2, and so on. Sequences defined in this manner are said to be inductively or recursively defined. Okay, next. Okay, in part 3,1,2, there is an example. In the point A, if B element real number sets, the sequence B equals B, 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 and so on, all of those terms equals B, is called the constant sequence B. Thus, the constant sequence 1 is the sequence 1, 1, 1, 1, 1, 1, and so on, and the constant sequence 0 is also 0, 0, 0, 0, and so on. And in the point B, if B element real number sets, then B equals B over n. Sorry, B equals B power n is the sequence B equals B, B power 2, B power 3, B power 4, and so on. In particular, if B equals a half, then we obtain the sequence 1/2 power n for n element natural number sets. So it's equal a half, a quarter, 1/8, and so on. And the point C, The sequence of 2n for n element natural number sets of even natural numbers can be defined inductively by x1 equals 2, xn plus 1 equals xn plus 2, or by the definition y1 equals 2, yn plus 1 equals y1 plus yn. Okay, next. Okay, the next part is the limit of a sequence. The definition of limits of the sequence: a sequence x element a sequence x equals xn is in real number set is set to converge to x element real number sets, or x is said to be a limit of xn if for every epsilon greater than 0 there exists a natural n k epsilon such that for all n greater than equals to k epsilon, the terms xn satisfy absolute value of xn minus x less than epsilon. If a sequence has a limit, we say that the sequence is convergent. If it has no limit, we say that the sequence is divergent. Okay. Part 3.1.4, there is a theorem of uniqueness of limits. The theorem said a sequence in real number sets can have at most one limit. Okay, there is a proof. Suppose that x epsilon and x double xn are both limits of xn. For each epsilon greater than 0, there exists k xn such that absolute value of xn minus x xn less than epsilon over 2 for all n greater than equals to k xn, and there exists k double xn such that absolute value of xn minus x double xn less than epsilon over 2 for all n greater than equals to k double xn. We let k be the larger of k xn and k double xn. Then for n greater than equals to k, we apply the triangle inequality to get absolute value of x xn minus x equals to absolute value of x xn minus xn plus absolute value of xn minus x double xn, which less than absolute value of xn minus xn plus absolute value of xn minus x double xn, which less than epsilon over 2 plus epsilon over 2, which equals epsilon. Since epsilon greater than 0 is an arbitrary positive number, we conclude that x xn minus x power x double xn equals 0. Okay, then for x elements real number set and epsilon greater than 0, recall that the epsilon neighborhood of x is the set we denote v epsilon x equals the set of u element real number set where absolute value of u minus x less than epsilon. Since u element of epsilon neighborhood of x is equivalent to absolute value of u minus x less than epsilon, the definition of convergence of a sequence can be formulated in terms of neighborhood. We give several different ways of saying that a sequence xn converges to x in the following theorem. Okay. The next theorem is also about the limit of sequence. Let x element xn be a sequence of real numbers, and let x element real number sets. The following statements are equivalent. Point A, x converges to x, and B, for every epsilon greater than 0, there exists a natural number k such that for all n greater than k, greater than equals to k, the terms x and satisfy absolute value of xn minus x less than epsilon. See, for every epsilon greater than 0, there exists a natural number k such that for all n greater than equal to k, the terms xn satisfy x minus epsilon less than xn less than x plus epsilon, and plus for every epsilon neighborhood v epsilon x for of x, there exists a natural number k such that for all n greater than equals to k, the terms xn belongs to v epsilon x. Okay, there is the proof, the equivalence of a and b. Uh, we know that the point a and b and just a definition from limit of sequence. And for equivalence of b, c, and d, we can write it like this: absolute value of xn minus x less than epsilon. It means, or it implies, minus epsilon less than xn minus x less than epsilon, which implies x minus epsilon less than xn less than x plus x, x plus epsilon, I mean, and it means xn also element of p epsilon x. Thus, it proves the equivalence of the theorem. Okay, from this part, we will explain by Dwi.
Thank you, Ilham. I will explain about example 3.1.6. Sorry. Limit 1 over n is equal 0 if epsilon greater than 0 is given. Then 1 over epsilon greater than 0. By the Archimedean property 2.4.3, there is a natural number k is equal k epsilon such that 1 over k is less than epsilon. Then if n greater than or equals k, we have 1 over n less than or equal 1 over k less than epsilon. Consequently, if n greater than or equal k, then an absolute value 1 over n minus 0 is 1 over n less than epsilon. Therefore, we can assert that the sequence 1 over n converge to 0. For example 3.1.7, the sequence of 0 to 0, 2, and so on does not converge to the number 0. If player A asserts that 0 is the limit of the sequence, he will lose the k epsilon came when player B gives him a value of epsilon less than 2. To be definite, let player B give player A the value epsilon 0 is equal 1. Then no matter what value player A choose for k, his response will not be adequate, for player B will respond by selecting an even number n greater than k. Then the corresponding value is xn is equal to, so that absolute value of xn minus 0 is equal to greater than 0 is equal epsilon 0. Thus the number 0 is not the limit of the sequence. Then is tiles of sequence. With definitions, if x is equal x1, x2, and so on until xn and so on, is a sequence of real numbers, and if m is a given natural number, then the m tile of x is the sequence. Xm is equal xm plus n for n element of natural number is equal xm plus 1, xm plus 2, and so on. For the next is the theorem for 3.1.9. Let x is equal xn for n element of natural number be a sequence of real number and let m element of natural number. Then the m tail xm is equal xm plus n with n element of natural number of x converge if and only if x converge. In this case, limit xm is equal limit x. For the proof, note that for any p element natural number, the p the p term of xm is the p plus m term of x. Similarly, if if p greater than m, then the key term of x is the key minus m term of xm. Assume x converge to x. Then given any epsilon greater than 0, if the term of x for n greater than or equals k epsilon satisfy absolute value of xn minus x less than epsilon, then the term of xm for k greater than or equal k epsilon minus m satisfy absolute value of x key minus x less than epsilon. Thus we can take km epsilon is equal k epsilon minus m, so that xm also converge to x. Conversely, if the term of xm for k greater than or equal k epsilon satisfy absolute value of xk minus x less than epsilon, then the term of x for n greater than or equal k epsilon plus m satisfy absolute value of xn minus x less than epsilon. Thus we can take k epsilon is equal km epsilon plus m. Therefore, x converge to x if and only if xm converge to x. For the theorem 3.1.10, let xn be a sequence of real numbers and let x element of real number. If an is a sequence of positive real number with limit an is equal to, and if for some constant c greater than 0 and some m element of natural number, we have absolute value of xn minus x less than cin for all n greater than or equal m. Then it follows that limit xn is equal x. For the proof, if epsilon greater than 0 is given, then since limit an is equal 0, we know there exists k is equal k epsilon over c, such that n greater than or equal k implies an is equal absolute value of an minus 0 less than epsilon over c. Therefore, it follows that if both n greater than or equal k and n greater than or equal m, then absolute value of xn minus x less than or equal can less than c epsilon over c is equal epsilon. Since epsilon greater than 0 is arbitrary, we conclude that x is equal limit of xn. Then for example 3.1.11, if a greater than 0, then limit 1 over 1 plus na is equal 0. Since a greater than 0, then 0 less na greater than 0 less than 1 plus na, and therefore 1 over 1 plus na greater than 0 and less than 1 over na. Thus we have absolute value of 1 over 1 plus na minus 0 less than or equal 1 over n times 1 over a times 1 over n for all n elements of natural number. Since limit of 1 over n is equal 0, we may invoke theorem 3.1.10 with c is equal 1 over a and m is equal 1 to infer that limit of 1 over 1 plus na is equal 0. Okay, I think enough for our presentations about the sequence and their limits. Thank you very much for watching this video. Wassalamualaikum warahmatullahi wabarakatuh.